So this chapter is all about energy, and let's talk about force and potential energy. Now, often we learn about lots of types of energy: kinetic, potential, heat, chemical, nuclear, and the sum total of all of them is conserved. But when reduced to the motion of particles, classical physics really has only two forms of energy: kinetic and potential. Best way to derive the conservation of energy is to jump right into the formal mathematical principles and step back, see what we have. The basic principle, call it potential energy principle, asserts that all forces derive from a potential energy function denoted by V of x. Recall that x represents the intercept of three coordinates. So let me just write it. So according to potential energy principle, the force on the particle is related to the derivative of the potential energy. So derivative of potential energy with respect to position. In one-dimensional case, the call this as one. Potential energy principle is just a definition of V of x. Potential energy can be constructed from the force by integrating the force over t of x, which is the position. Now call this as second equation. So what does this mean? So you can think of the first equation as like this: the force is always directed in a way that pushes the particle toward lower potential energy, not the minus sign. So the rate of change of potential energy with respect to position, and especially the change in the opposite direction, which means as this increases. So as the position increases, which means this decreases, the force is also decreasing, and force pushes you down the hill. Basically, that slogan you can keep in mind. And so now remember too that as potential energy increases, kinetic energy decreases. It's kind of inversely proportional. Kinetic energy denoted by T. So this is again potential energy. So it's kinetic energy denoted by T. Of course, the formula is just half v square. And the energy of a particle just half mv square plus potential energy of it. And you could say that the rate of change of kinetic energy, we can assume that if mass is constant, but v square can vary. So we could call it as the rate of change of kinetic energy as mass times velocity times the rate of change of velocity. Because remember too, this is the energy. So energy, the energy is just force times. So if m and this is acceleration, this is mass, this is force times velocity. The units of uh, rate of change of energy are this force times velocities. So it can also be written as mva. And this dot, as I've said multiple times, is denotes the rate of change. Now reduction of time, and we can calculate the rate of change of potential energy as well. Let's do that. dV by dt. Now, if you remember the partial differentiation derivatives, so we can write it like this. Now, they do cancel each other out, and fortunately for us, this becomes just v. So this is just dV by dx times just velocity. Don't confuse the small v with the large v. Of course, this potential energy, this is velocity. Now, as we know that energy is just t plus v, right? So the rate of change of energy would be equals to rate of change of kinetic energy plus rate of change of potential energy, which means, as we have those equations already, that would be like this. So it could also be written like v of ma minus f x, because recall that the potential energy is just equal to force in the opposite direction times the velocity. And now, so far we spoke about something in just one dimension. So what about we go more than two dimension? Let's see now. So if you write equations of motion, then the rate of change of position two times, which is with respect to time, d square of x by dt square, as we know, is just force. This we have seen already. And we also in the one-dimensional case that the force is minus derivative and all that now. So if we were to extrapolate this the force that we saw, the force and the potential energy equations, we can write it like this. This is a partial derivative, and yeah. What so let's visualize what this means. Picture a terrain with the function v of x representing height or altitude at each point. Now minus sign represents the force points in the downhill direction, and it also says that the force is greater along the directions where the slope is steeper, so inversely proportional to the position. And on the contour map, there is no force pushing all the contour lines. This force is vector points perpendicular to the contour. So let's come back and derive energy conservation. To that, just to plug in check that equation that we got already. So this is energy conservation equation. Now let's multiply each of them by rate of change of position, and let's just take a look at so if we do various equations here, we will come to a conclusion that the potential and kinetic energy, if we were to add them, we will get zero. It's kind of an important equation. Now you might wonder why the forces of nature are always gradients or derivatives of a single function. Well, in the next chapter, we will reformulate classical mechanics using the principle of least action. In this formulation, it is built in from the very beginning that there is a potential energy function. But then why the principle of least action? Ultimately, the answer can be traced to the laws of quantum mechanics and the origin of forces in the field theory. Subjects that for now we will just not go deep into, because that's not the subject of the book. And well, there are some other forces as well. other energy types like mechanical energy, heat, chemical energy, atomic nuclear energy, electrostatic energy, magnetic energy, radiation energy. Now they're kind of combination of kinetic and potential. For example, mechanical energy just is just like kinetic and potential energy of large visible objects like planets or weights being hoisted by a crane. And the heat is heat energy or just heat is just collection of molecules and the kinetic and potential energy of those molecules. So the only difference is that it involves the large and chaotic motion of so many particles that we don't even try to follow the kinetic and potential energy in detail. Chemical energy is also a special case. So the energy stored in the chemical bonds is a combination of potential energy and kinetic energy of the constituent particles that make up the molecules. And electrostatic energy is another word for potential energy associated with the forces of attraction and repulsion between electrically charged particles. So, in fact, so yeah, everything is just a potential and kinetic energy. So, in fact, so much that apart from gravitational energy, it's the primary form of potential energy in the ordinary classical world. Oh, okay. So the electrostatic energy is the primary force of energy, primary form of potential energy apart from gravitational energy. So I mean, so the grav comes first, and then comes electrostatic energy. So this is like number one, two in terms of primariness. And magnetic energy is kind of tricky, but the force between the poles of magnets is a form of potential energy. And finally, the energy stored in electromagnetic radiation. Those comes from photons, isn't it? So the energy is stored in the 3D waves, the photons, and it is the combination of kinetic and potential energy, but it's not the energy of the particles, not unless we get into the quantum field theory, but of the fields. So when we talk about photons, they obviously don't have mass, so we cannot talk about potential and kinetic energy of photons. So it is of the fields, which now the field thing comes into the quantum mechanic subject, which we will see in a later book. That completes this chapter. Chapters in this book are very simple, as you see. It's mostly equations. It's literally theoretical minimum. Understanding of these equations is all that's the goal of this series.